it works. It's working.
Yep. Okay.
At least we're gonna, it has to be a five. That's true. I'll ask you one more question. Yeah, true.
Wait, could everyone sign? Does everyone sign the attendance form?
Okay. I think there's like a lot of latency. Well, hi everyone, welcome to the Math1081 workshop today. I'm Steve and I'll be presenting topic 1 for you guys. We'll be doing some past paper questions. So yeah, and can I get a confirmation from the YouTube stream that audio is okay? Oh. So I feel like there's a bit of a latency for the YouTube stream, about like 10 seconds. So yeah, sorry about that, but I'll just continue. So I'll be covering topic 1 right now, sets, functions, and sequences. So let's jump in. So this is a question from 2019, and it says, let f be a function from a to b, and g be a function from b to c, and consider the statement, if g is injective and g composed with f is surjective, then f is surjective. So, okay, and the questions are, well, we're given a false proof apparently, with that some other student has given, and for part B we have to prove that the statement is true. So I'll just copy paste this. So this is the question, and okay. So before we jump in, we should revisit the definitions of an injective function and a surjective function, right? So, okay, so what does it mean for a function f to be injective? Well, okay, so let's say we have a function f, f from a to b. So what does it mean for this to be injective? Well, let me draw the sets out first. So f is from the sets, okay, for this circle. A. And what does it, the meaning of the definition of injectivity is that for every input you get a unique function value. So if we start from a point A, we're going to go to some point in B, and no 2 points in A will lead you up to the same point in B. So we can have these two, that's fine, but we can't have, say, a third one from here going to either of these two. We can't have that. Yeah, that's injective, and the definition for surjective is a bit different. And okay, let me draw up the sets again. So if f from A to B is surjective, then let's draw the sets again. That means we can choose anything in the set B, and we're guaranteed to have an arrow coming from A going to it. But it doesn't matter what we choose in B, there's always something in A, so that f of that something is that point we chose. And that's a simple definition. So, okay, let's just jump into the question. So apparently there are some incorrect stuff with this proof, but let's have a read first. So it says, let f be a function from the integers to real numbers where fx equals x, and let g be a function from the real numbers to the real numbers where g of x equals x cubed. Then g is injective, and also g composed with f of x equals gfx equals gx, and so g composed with f equals g, which is surjective. However, f is not surjective, and so this counterexample proves that the statement is false. So apparently there's something wrong with this, and the way we're going to find the incorrect part is going through step by step. So the first part's fine, it's just defining some functions. There's really nothing that can be wrong with that. And so the second part is, the student says g is injective. We should confirm that, right? So g of x, they say g of x equals x cubed. They say that's injective. And so how do we know if it's injective? Well, we can actually look at the graph of this function, which is pretty simple. Just a cubic function. If you see carefully, like if you're going to give, well, every input is going to result in a different output, right? So if we pick a point, like we can't pick 2 points where the function values are equal at those 2 points. And that's why it's injective. And another way you can test it is like using the horizontal line method. If any horizontal line crosses the function or the graph at one point, then it's injective. So yeah, that part is fine. So g is injective, that's fine. And okay, the next part is g composed with f of x equals g of f of x equals g of x. And okay, let's confirm that as well. So what's g composed with f? So g composed g composed with f of x. Well, the definition is that just equals g of f of x. Yeah, that's fine. But what does fx equal? So fx was defined to be x. Yeah, and so we can just substitute the fx with x in our equation. And so that part is fine. So g of f of x equals g of x. And also the next part is, because of that, the student concludes that g composed of f is g. Like the functions are equal in this sense. And is this correct? Does anyone have a guess? No? Huh? Yeah, so okay, so the answer is, well, these functions are not equal because the domains are not equal. So if you look at g composed with f, right? You're feeding input to f first, and then g is taking that input, since it's g of f of x. You're giving a value to the function f first, and then g is taking the output of f. So the domain of g composed with f is the integers, because f takes numbers from the integers. On the other hand, g, right? G by itself is from the real numbers to real numbers, so it has a different domain, and that's why these functions are not equal. And because of that, the rest of the proof doesn't make sense, because it's relying on this assumption. Yeah, so that's that question. And okay, so the next part is we have to prove the statement is true. And the statement is, I'll get it back up. This is a statement, and we have to prove that the statement is true. And so, to prove that the statement is true, we have to assume what we're given first. And what are we given? We're given that, we're given that f is a function from a to b, and g is a function from b to c. That's our first assumption. So suppose f, oh my goodness, f is a function from a to b, and g is a function from b to c. That's our first fact. We have to suppose that. And what else do we have to assume? Well, we're given that, well, we're not given, well, okay, so to prove an if and then statement, we have to suppose what the if condition is. And the if condition here is if g is injective and g composed with f is surjective. So we also suppose that. Suppose that g is injective and g composed with f is surjective. And to prove this if-then statement, we have to somehow go through a series of steps and reach the conclusion that f is surjective. And so to prove that f is surjective, we have to use the formal definition of surjectivity. And the formal definition is that for every, okay, so we have to show that for every y in B, there exists x in A, so that f of x equals y. This is just a really formal way of saying to prove that f is surjective, we have to show that choosing anything in the codomain is going to be a function value. And okay, so now this is another kind of if-then. So it's like if, it's for every statement, you can translate that into if y is in B, then there is an x in A so that f of x equals y. So we have to suppose, suppose y is anything, y is in B. And we have to just find x so that f of x equals y, where x is in A. Now, we have to use our facts that we supposed before. So, and the facts are, I'll just scroll up. The facts are that f is a function from A to B, g is a function from B to C, and g is injective, and g composed with f is surjective. And so, which of those facts would be useful for the first step here? So we only have y is in B. Which fact should we use? Does anyone want to guess? No? Okay. Okay. So this might be really obvious that you might not notice, but g is a function from B to C, and so g of y must be in C, right? Because g is from B to C and y is in B. should write then. Right, so yeah, that's the first step. And okay, so what should be the next step using our facts here? G is injective and G composed with F is surjective. Right? Before we do that, I think I should give you the formal definition of injectivity and surjectivity. The formal definition for injectivity is if F is, well, not F. If F from A to B is injective, then if x1 and x2 are in A and f of x1 equals f of x2, then x1 equals x2. In other words, if the outputs are equal, the inputs must be equal. And for surjectivity, or I think we went through the definition, for surjectivity, if f from A to B is surjective, then for every y in B, there exists x in A, so that f of x equals y. Right? Now, if we apply these definitions to what we're given, we know G is injective and G composed with F is surjective, meaning that the G is injective. So if y1, y2 are in B and G of y1 equals G of y2, then y1 equals y2. That's the first fact, very formally stated. And the second fact was G composed with F is surjective, meaning for every Z in C, there exists X in A, such that G of F of X equals Z. So I'll just label these. So what were we up to in our proof? So we know G of Y was in C. And it looks like we can apply the second fact here, right? Because G of Y is in C, there is an X in A, so that G of F of X equals G of Y, right? It's like substituting a Z in this fact with the GY. So using our fact, since G composed with F is surjective, there exists X in A such that G of F of X equals G of Y. Right? So that's using the second fact, we got this result. Now, so the next step will be using fact 1 here. And fact 1 is based on G being injective, and the y1 and y2 in our fact here can be substituted with the fx and y here. Because fx and y are both in B, and G of fx equals G of y. And that means, using G is injective, since G of fx equals G of y, we must have that f of x equals y. And if you notice, this is what we're actually trying to get to, right? We found an x so that f of x equals y. And that means Okay, so we just found an x in A such that f of x equals y. And if you remember, y was pretty much anything in our set B. Right? So, so y was anything in B. But this means for anything in B, we found an x in A so that f of x equals y. And so by definition, f is surjective. Since we found an x in A so that f of x equals y for any y in B. And yeah, that's the end of proof. Let me just put the square here. And that's the proof. Are there any questions? No? All right. So next question is from 2018. And okay, so let A be a set with 5 elements. And it says, well, part A just says, find the cardinality of the power set of A. So what is a power set? Power set is just a set of all subsets of A. And that might sound really confusing, but no, it's just, so if you want to build a subset of A, sorry, 1 second. So power set of A is set of subsets of A. So for example, if A is 1, 2, then the power set of A is the set of all subsets. So what's one subset of A? It's an MC set. Another subset is just the 1. Another subset is the 2. And the final subset is just A itself. And it's a set of sets. And there's a formula for finding the size of a power set given the size of the original set. And that's just, the formula is the size of the power set of A is 2 to the power of the size of A. And if you think about it, it's like if you're building a particular subset of A, then for each element you have 2 choices. You're either going to include it in your subset or not include it in the subset. And that's why, that's the reason for the 2 over here. And the power, that's the reason for the 2 here. And the power of the size of A is just, you're doing that decision for every single element of A. And so in our question, the size of A was 5, so the size of P of A equals 2 to the 5, which is 32. So, in the second question, we're going to skip B because it was not really topic 1. So we're just going to do C. In the C, it asks us a question. Is the function f from the power set of A to the power set of A given by f of s equals s complement surjective? It says prove your answer. So this question doesn't really say like, prove that this is true or prove that this is false. We have to decide for ourselves first and then prove. So we need to take a guess. Is this statement true or false? What do you think?
True.
Okay. If we think it's true, we should just, we should stick to that and try to prove that it is true. So how do we prove that this is true? Well, okay, let me copy paste. Alright, so we decided that this statement is true, so we're proving prove that f from PA to PA, where f of s equals s complement, is surjective. Now, we did this kind of problem before. We proved some function is surjective before, so how should we start? Does anyone have any ideas?
State some definitions.
Yes, exactly. We need to state some definitions. Sorry. So we have to state some definitions. So, okay. What will be the first definition we should state?
The definition of a surjective function.
Yes. Okay. So we should define what a surjective function is. So what we need to prove is to prove that fs is surjective, we have to show that for any or for every set, say y in the codomain of f, there exists let's say x in the domain of f, which is still the power set of a, such that f of x equals y. We just have to find one, right? For any element in the power set of a, we just have to find another one in the power set of a, so that the function value at that the function value of x equals y. So f of s was s complement, right? So if f, so we need to find some question mark so that f of that question mark equals y. I should really state, before that I should suppose y is in the power set of a. We just need to find this question mark and see if that's also in the power set of a, right? And does anyone want to take a guess of what that question mark would be? Yeah, so y complement works. Y complement works because f of y complement is y complement, which is y by the double complement law, if you remember that law. And yeah, and is y complement in the power set of a? Well, in our case, the y complement would be a minus y. A is like our universal set here. And if you think about it, if you remove any elements from A, then you automatically create a subset of A. And that's why y complement is also in P of A. So, yes. And so, okay, this is a really informal way of proving it, but we have just shown that for any set y in PA, there is y complement in PA, such that f of y complement equals y. And that's why f is surjective. Okay, so that's the proof, and that's the question done. Any questions? No? All right, sorry, 1 second. Alright, I think we're running short of time, so I'll skip to topic 5, which is graphs. And yes. So, okay. This question is from 2019, and okay, there's a pretty big graph with like 9 vertices. And the first question is, does G contain an Euler path? Give reasons. And okay, so an Euler path, if we forgot the definition, is just it's a path that goes through every single edge of the graph. And the question is, does G contain such a path? Well, there's a really neat theorem that you probably learned in the lectures. It's the Euler's path theorem, and it says a connected graph G has an Euler path if and only if there are exactly two vertices of odd degree. And yeah, so the only task we have here is to count all the odd degree vertices. And it turns out, it turns out Y has 3 vertices coming out of it, and that means it's degree 3. That's an odd degree vertex. Same with X. X has degree 3. W has degree 4. V has degree 5. Wait, we just found 3 vertices that have odd degree. And so using this theorem, we know that there is no Euler path. Right? We don't have exactly 2 vertices of odd degree, and so G does not have an Euler path. And next question is, it says show that G is a bipartite graph. So what does bipartite mean? A graph G, well, this is a formal definition. It says a graph G is bipartite if there are 2 disjoint sets V1 and V2. Disjoint means no common elements, and such that V1 union V2 equals V. So it's a partition that covers all of the set of vertices, and every edge of G connects a vertex in V1 to a vertex in V2. And the informal way of saying it is, if a graph is bipartite if you can split the vertices into 2 groups so that every edge makes a bridge between the 2 groups. I'll show you. So if G is bipartite, then we can split the vertices into 2 groups. And let's say we have 2 of them here and 3 of them here. And if it's bipartite, every single edge has to be a bridge between these 2 groups. So like we can have this one over here, this one over here, this one over here, but we can't have something like this. It doesn't make a bridge between the 2 groups. That's what bipartite means. And our task is to show that the graph G is bipartite. I'll copy paste the graph here. So we have to show that this is bipartite, and to do that, we just need to find a way to split the 9 vertices into 2 groups, so that every single edge is a bridge between the 2 groups, just like we see here. And we're given that it is bipartite, right? Because it says we have to show that it is bipartite. And the way to do that, there's a cool trick for this. You set up the 2 groups first, like this. So these 2 are going to end up being the 2 groups of vertices we split. And okay, we just look at one of the vertices, like say T, right? T is going to end up being in one of these groups, like either one. It doesn't matter where we put it in, it's going to belong to one group. So let's just put T in this group over here. But what does that mean? Every single edge has to be a bridge between the 2 groups. And so if T is here, its neighbors cannot be in the same group, right? T is a neighbor to V and S, and so V and S must be in the second group. Otherwise, if V was in the same group as T, then we'll have a bridge. Well, we won't have a bridge, right? The edge won't be a bridge between the 2 groups. Okay, and we just keep going. Like we just repeat for the vertices we just added to the other group. So for V, the neighbors are W, Y, P, R, and T, right? That means W, Y, P, R, and T cannot be in the same group as V, right? So W, Y, P, R, and T is already here. They must be in this group. And we just repeat for, say, S. For S, the neighbors are T, W, Y, and R. And yeah, I think they're already part of the other group, so we don't do anything about that. We just move on to the first group again. We look at W and see its neighbors. Its neighbors has to be in the other group. So again, W has neighbors V, S, Q, and X. And it looks like Q and X are not part of the second group yet. So let's add them in. And we can stop here because we covered all the vertices already. There are 9 vertices in total. We have 5 in one group and 4 in the other. And yeah, so the reason why, so we have shown that G is bipartite as the vertices can be partitioned into 2 say sets. For example, what do we have? TWYPR. And the other was VSQX. So that every edge, well, I'm just going to informally say it, is a bridge. Between the 2 sets of vertices. And yeah, that's part B done. G is bipartite. And the next question is more interesting. It says, prove that G does not contain a Hamilton circuit. And the Hamilton circuit is a circuit in the graph G where every single vertex is visited exactly once. Only exactly once. And okay. So there are no like real theorems, like really useful theorems for proving that a Hamilton circuit exists or not. And so we have to kind of do it manually per se. So, and part B is going to come in useful here. Okay, so okay. C. Prove that G has no Hamilton circuit. So we're going to have to use the fact that G was bipartite from before. And I'm going to bring the groups back up, the vertex partition for our bipartite graph. And I think it was WYPR. And the second group was VS or VXQS. All right. So let's try to prove this by contradiction. Let's say, maybe there is a Hamilton circuit here. There is a Hamilton circuit in G. And what does that mean, right? So what does that mean? Well, every single vertex, right, we're going to have to go through it because the Hamilton circuit goes through each vertex exactly once. And if it exists, then, well, in particular, it's going to have to go through T, right? So let's say, T has to be part of the Hamilton circuit. Now, what happens if we travel along an edge from T? since this is a bipartite graph, we always have to cross groups, right? From T, we're going to end up in this group of vertices, right? And moving from this group along an edge, again, will transfer us to the other group, right? Since every edge is a bridge. And if we keep doing this, so we keep doing this, 1, 2, 3, 4. We're eventually going to run out of vertices in our second group, right? Here we traveled along 1, 2, 3, 4, 5, 6, 7 edges, and we end up covering every single vertex in our second group of 4 vertices. And we can move back again, right? We can move back again from here, back to this group. So we covered every single vertex, but there's no way we would have came back to the same place we started from, right? We can't have ended up at T right now because this is our 5th vertex that we visit, the last vertex we visit in our first group. And yeah, and we also traveled through 9, wait, not 9, is it 9? 1, 2, 3, 4, 5, 6. So we traveled through 8 vertices, and we ended up covering 9 vertices, like 8 edges, covered 9 vertices, but there's no way we can come back to T, because to come back to T, we need an edge directly to T, but that's not possible because this is a bipartite graph. Every edge is from one group to another. We can't have a vertex back to T from here. And that's why G has no Hamilton circuit. And it didn't matter where we started from, because a circuit, there's no start point of a circuit. You can start anywhere, you still have to come back to that same place. We could have chose to start with Y instead, for example. And yeah, that's the proof. Well, you can't really write that in the exam. You have to state that in words, which is a bit annoying. But yeah, that's the sketch proof, I guess. So next question is also from 2019, but term 1. And says, let G be a connected simple bipartite graph with vertex partition V equals V1 union V2, where V1 equals the size of V1 equals the size of V2, and that equals n. And also suppose that every vertex has degree 4. And part A is determine the number of edges of G with explanation. And before we go on, does anyone have any ideas of what theorem or lemma we should use for this? Well, okay, there's a really useful lemma called the handshaking lemma. And it says for any graph with vertices V and edges E, and these are sets, 2 times the cardinality of E equals the sum of vertex degrees for every single vertex. And using this, we can find the size of E, which is the number of edges. So so we just need to know what the sum of vertices is here. Sum of vertex degrees. How many vertices do we have? Well, this is a bipartite graph where the partition of vertices, the 2 groups we split off into, they're both size n. So we have a bipartite graph, and there's n elements here, n vertices here, and n vertices in the other group. And so there are 2n vertices. I think it was a lowercase n, sorry. There are 2n vertices. And the question also says, very conveniently, that every single vertex has degree 4. And so the vertex sum, which is degree of V for every V in V, that's just the number of vertices times 4, because every single vertex has degree 4. So that's 2n times 4, which is 8n. That's the number of vertices. But using the handshaking lemma, which was 2 times, write in words, num edges, equals this vertex degree sum, which happened to be 8n in our case. And so, just dividing by 2 on both sides, we have the number of edges is 4n by the handshaking lemma. And yeah, that's part A. So we have 4 n edges. And part B is prove that G is not planar. And okay, so what does planar mean? The definition of a planar graph is actually really, really informal, and that is actually the formal definition. So it's planar if you can draw it in 2D without crossing edges. Like, that is literally the definition. And okay, and there's a really useful theorem that we should use for this. And it says if G is a connected planar graph with E edges and V vertices, where V is greater than or equal to 3, then either E is less than or equal to 3V minus 6, or E is less than or equal to 2V minus 4 if G has no cycles of length 3. And this theorem is really useful for proving that our graph is not planar using the contrapositive, which is from topic 3. And the contrapositive is pretty much, it's like we get to flip an if condition. Like if we have a statement, if A then B, this is the same as if not B, then not A. And in our case, let's just try to compute one of the inequalities first. So we know E is 4n from part A, V is 2n from part A as well. So is this true? Wait, no. So we have E is greater than 2V minus 4, right? Because 2V minus 4 is 4n minus 4, and that has to be smaller than 4n, which is E. E is greater than 2V minus 4, and also we can actually show that G has no cycles of length 3. And in exam, like, we wouldn't be able to just say that. We have to show why. And the reason why G is bipartite is because, or not bipartite, has no cycles of length 3. It's because it's bipartite with n vertices here and n vertices here. And remember, bipartite just means that every edge acts as a bridge between these two groups. So no matter where we start from, let's say the first group, if we travel along 3 edges, like 1, 2, 3, we're never, like, it's going to be impossible to end up back at the same place to create a cycle. And that's why there are no cycles of length 3. And so we just showed that E is greater than 2V minus 4, and G has no cycles of length 3. And so by the contrapositive of this statement, G is not planar. And yeah, that's it. That's it for that proof. Any questions? So definition of a planar graph. A graph is just planar if you can, like, literally draw it in 2D without crossing the edges.
So like when we say by the positive of that theorem, would you just say by the definition? Like, or would you just state that?
I think this theorem doesn't really have a name, so yeah, it's a bit hard. I think you should name the theorem and then say by the contrapositive of that theorem, this is true. But if this theorem had a name, say planar graph theorem, then you can just say the contrapositive of the planar graph theorem, something like that. Is that okay? All right. So next question is about spanning trees. It says consider this weighted graph. And yeah, it looks a bit weird, but whatever. Part A is use Dijkstra's algorithm to find a spanning tree that gives the shortest path from A to every other vertex of the graph, and make a table showing the details of the steps taken when applying this algorithm. And so the algorithm is, in my opinion, like, pretty complicated, and I have my own way of doing it, but I'll just read this out. And it says, okay, so first step is just to define a set T and just put the starting vertex A in it. And then second step is let A be a set with edges in one vertex in V and not one vertex V not in T and the other in T. And then choose an edge E from A that gives a shortest path from A to any V, and then add E to T and continue until T contains and like blah blah blah. It's a bit confusing, but I'll demonstrate to you, and it doesn't seem that complicated if you draw it out. So let me copy paste graph. Right. So the visual way. So to use Dijkstra's algorithm, we have to start from the vertex that we're told to start from, which is A. So A. Let me use. So we're starting from here. And the way Dijkstra's algorithm works is we get every single edge that's connected to the spanning tree we have right now. And the spanning tree we have right now is just this point A. And the edges, we call them candidate edges, all the edges that come out from the current spanning tree, which is AB and AD. It's like adding a branch to what we already have. The set of all edges that are like the next branches. And so we make a table with one column called candidate edges, and another column called selected edge. And the candidate edges for now is just A, AB, and AD. And when we mention candidate edges, we also give them a number. We assign them a number, and I'll demonstrate first. We assign them a number, and for AB it's 2. And this 2 just represents the distance from our starting point to this edge. Not this edge, this vertex. And that's just 2 right now, because from A to B is just the edge weight 2. And for AD, similarly, it's 6. And for every step, we always pick the edge that has the smallest value here, the smallest value that we assign it to. And we put it on the selected edge. We select A, B. That's part of our current work in progress spanning tree. And then we repeat. I think I should erase this. Whatever. Okay, so next up, we get the next candidate edges. And the candidate edges this time are AD, and then BD, BE, and BC. It's just adding an edge that would extend this spanning tree by 1. It's like, and that's kind of how the original algorithm stated. It's like, let A be the edges with one vertex in V, and V is like one vertex V in T, and T is like our current spanning tree that we're working on, and the other in T. So right now, our T is like the red part here, and our A is all the blue edges I just highlighted. And so for all of these, we do a similar thing for assigning values. Okay, so Right now, AD would remain 6 because if we travel along the spanning tree we have right now, as well as AD, we're going to end up with a distance of 6 to D from A. What about for BC? Now, we don't put 2 here. It's not 2 here because we're not just putting in the weight of that edge. The number here represents the total distance that we would travel to C from A along our current spanning tree we have. So we have to go through A, B, and then C. That means the number we assign here is not 2, it's 4. Because we have to travel from A, B, and then C using our current spanning tree right now. And similarly for the other edges, this line is running out of space. BD, for example. So if we travel along the shortest, not the shortest, if we travel along towards D using our spanning tree and the edge BD, then we'll get a total distance of 5 to D. If this is a bit confusing, we can have another column, say selected vertices, or selected vertex. And the selected vertex is just the endpoint of the edge we select. The number here makes much more sense now. It's pretty much if we travel along the spanning tree to B and then B to D here. That gives us a weight of 5. And similarly, what's the next edge? BE. BE would be going from A, B, and then E, so 8. Travel along the red part and then the blue part. And out of those, we select the lowest value, which is BC. And maybe just ignore the selected vertex part for now. And then we would keep going, and which one do we select? BC. And then our next set of vertices, candidate edges, candidate edges, we will include C to E and then C to F as well as I think C to D. Yeah, these are all our candidate edges, and for each of these we have to find the smallest value. And most of these are already from the last step, so I'm just going to detour them. And then what did we add? We added CD. And CD is traveling along our spanning tree, which is A, B to C, and then D. So that's 2 plus 2 plus 2. Yeah, that's 2. So CD is 6. Just say that again. Going through the red parts first, and then using the blue edge, C to D. And that's 2 plus 2 plus 2, and that's why it's 6. And another edge is C to F. And for that, it's just 2 plus 2 plus the weight of CF, which is 1. And that's 5. And similarly for CE, I forgot. For CE, it's 2 plus 2 plus the weight of CE, which is 3, so 7. And I think those are the edges we added. That's the additional edges, and there are some edges that are from the previous step we didn't select. So like AD is still here, and BD is still here, which is 5, and BE is also here. And out of these, we just select the smallest one again, which is CF with 5.
Why do you write like in the second step, why do you write
For the second step, you mean when we selected BC?
I get that. Just like why do you write
Because it's a candidate edge. And a candidate edge is just, like if we take one step from our current spanning tree, which is red, like, how do I say it? It's like an extra branch. If our spanning tree were to grow an extra branch, right?
I thought it was just one thing.
No, it's everything from the whole of the spanning tree. Yeah. And yeah, so the AD is here. Right, where were we? We chose CF, which is the smallest one here, and then we just continue.
So there's also BD, right? Which is also 5.
BD. Yes. And okay, if you end up with 2 of the same values, then you can choose either one. Doesn't really matter. Yeah, you will end up with a different spanning tree maybe, but it will still be a spanning tree.
So don't choose both, just choose one.
Yeah, just choose one.
Just choose one.
Yeah. Well, I mean, yeah, sometimes like you might be able to choose 2 along the way. Like if you might end up choosing both, like not necessarily. And we'll just get through. We probably would choose BD in the next step, I think, though. Okay, so the next one was CF. Where's my pen? And now we need an extra candidate edge, which is FE. So basing off the current spanning tree, it's like one branch growing, like one step of growth, like of one edge. And it turns out we're just adding FE here. FE is, we go along the spanning tree, so 2 plus 2 plus 1 along the red, and then along FE, which is 1. So 2 plus 2 plus 1 plus 1 ends up being 6. And the rest, honestly, like everything from the previous step kind of stays except for CF, which is the one we chose. So let me just print for ditto except CF, because we already chose that. And if we do that, BD ends up being the next vertex we choose, next edge we choose, because it has value 5, and that's the smallest one there. That's our next step. So BD. And okay, we keep continuing, and so, but this time our candidate edges change a bit, because another requirement for getting the candidate edges is to see if adding that candidate edge will cause a cycle. And since a tree can't cause a cycle, we can't pick vertices that will make a cycle in our spanning tree. For example, if we can't choose AD now, because that will create a 3 cycle, A, B, and D, in our spanning tree. And so it ends up, oh wow, that deletes the whole thing. I'll just use a different color now.
Does that mean we can't choose D and C as well.
Yeah, because that'll create B, C, and D as a cycle. Yeah, correct. Which color should I use? Green. Okay, so our next candidate for edges are, okay, so this one, E and F is still fine. It's not going to cause cycles. Where's my pen? This one's fine. C and E is also fine. It looks like it's not fine because of E and F, but E and F is also a candidate edge, so it's fine. C and D is not fine, as we said before. B and E is good. D to E is also fine. And A and D is not fine because it will create a cycle, as we said before. And so in this step, so let's look at FE first. So FE, it's still going to be 6 from our last step. So 2 plus 2 plus 1 plus 1. And it's another one, C to E. I think C to E was there before as well. C to E is 7, 2 plus 2 plus 3. And B to E. Let me just copy paste this. B to E's, what's that number there? 2 plus 6. If we go along the spanning tree first and then E, B to E. So 2 plus 6 is. And another one, DE. I think that's the final one. DE would be 2 plus 3 plus 3, so 8 as well. And out of these, we choose the smallest one, which is FE. And we stop here because we covered every single vertex of the graph G. And yeah, the red part is a resulting A part spanning tree is what you call it. So yeah, using Dijkstra's algorithm, we get to find the shortest path from A to any other vertex. For example, shortest path from A to D turns out to be A, B to D, which is 5. And then from A to E, it turns out to be a cost of 6, so 2 plus 2 plus 1 plus 1. Yeah, and that's the answer for part A. Yeah, I think we've gone over time for my part, so I'll let Felix take over for topic 2. Yeah, thanks guys. It's the same thing. This is the comments.
We'll just take a 2-minute break for now.
Okay, so can I draw on my slides? Is that possible?
What, you have to use this?
Yeah, but like, can I draw on the slides?
Sorry, what's the
Okay, I should restart, right?
okay.
All right. Yeah, so as I was just saying, right now we're just testing numbers for this question, and we've gotten up to 7 squared, which is 49, and because that's such a large number, we sort of want to make the, I guess the modulus or the magnitude smaller by minusing 57 to get -8. But still, that's not 1, so we still haven't found our answer. We still haven't found our answer yet. Okay, so let's times this by 7. We're going to times -8 by 7 and not 49 because, you know, we've gotten -8, which is much nicer than 49. So if times -8 by 7, we get -56. And right now, when you look at -56, it's not our answer, right? But if we, you know, use the same trick as we did just then, we can plus 57 to it and we get 1, which is what we want. So we found an n, which is 3, and this satisfies this congruence. So 7 to the power of n is equivalent to 1 modulo 3, modulo 57. And so 3 works. Awesome. Okay, now let's dive into the second question. Hence or otherwise calculate this big ass sum. If we, the first thing you should do with sums is, unless it's either GP or an AP, is try to just expand it and see what it looks like. So I've done that here. So 7 to the 0 plus 7 to the 1, etc., all the way up to 7 to the 1000 in modulo 57. Normally, if this wasn't in modulo 57, we'd probably have to use a GP here. But because it's in modulo 57, we can expect that most of these values come down to a number between 0 and 57, because that's how modular arithmetic works. Okay, so as we know that 7 to the 0 is equivalent to 7 cubed, which is equivalent to 1 in modulo 57, we can sort of guess out that all the multiples of 3 in 7 to the power of any multiple of 3 is going to be equivalent to 1 in modulo 57, because we found that from part A. That's our use of the word hence. If we see that this sort of pattern recurs every 3 powers, we can apply it to 7 to the 1, which means that every, I guess, integer in this form, so 7 to the power of 3k plus 1, so 7 to the 1, 7 to the 4, is all equivalent to 7, sorry, not 0. And if we go one further to do 7 squared, which is equivalent to 7 to the 5, which is equivalent to 7 to the 8. And any integer in the form 7 to the 3k plus 2, that's equivalent to -8, as we saw before. Yeah, just a note, that 0 should not be 0, it should be 7. Sorry about that. And now that we have this pattern that occurs, now that we can see this pattern that occurs every 3 powers, let's apply it to here. So I've colored the repetition. So once you, I guess, do further calculation, you can see that 7 to the 0 equals to 1, 7 to the 1 is just 7, but 7 squared is equal to -8. And so every 3 of these numbers, we get a sum of 0, right? Because 1 plus 7 plus -8 is equal to 0. And this repeats with 7 cubed to 7 to the 5. And this goes all the way up to, I guess, what we want, right? 7 to the 1000. And as we can see here, our pattern stops when we reach 7 to the power of 998, because 998 is some multiple of 3, so that would be 996 plus 2, right? So we get zeros all the way up to 7 to the power of 998, not including that one. So what we're left with is 7 to the power of 999 and 7 to the 1000. So all we need to do is calculate those two, and we can have our answer. So as you can see here, all these sums go to 0, and we're just left with 1 plus 7, which is equivalent to 8 in modulo 57. So we've been successfully able to calculate the sum. Awesome. Now let's move on to the next question. Let A, B, Q, R be integers such that A equals to BQ plus R, where A and B are not 0. Prove that the GCD of B and R is less than or equal to the GCD of A and B. So if you actually take a closer look at this formula, A equals BQ plus R, that's quite a familiar formula, because this is what is known as the division algorithm, which specifies that if we're dividing A by another number, say B, we can write it as write the division as A equals to B times some quotient plus a remainder. So if we took A as 52 and B as, say, 10, right? 52 equals to 10 times 5 plus a remainder, which is 2. So now let's try to prove this. Oh yeah, so just a reminder that with all your proofs in your questions, you have to make sure that you start with some sort of indication that you're starting the proof. So what I've done here is just write proof, right? And we need to, with a proper proof, we need to assume what we need to prove, right? So in this case, we need to assume that A, B, Q, and I are integers, and this equation holds, because we're using that to prove, I guess, the GCD of B and I is less than or equal to the GCD of A and B. Okay, so now if we let D0 be the greatest common divisor of B and R, and let D be the greatest common divisor of A and B, we can see that quite clearly from just the definition of greatest common divisor that D0 divides B and D0 divides R. So that's quite nice, because if we look at our formula that we assume, because D0 divides B and D0 also divides R, it must divide 8 as per this formula. And so because we understand that D0 is the greatest common divisor, that means any other divisor of A must be smaller than or equal to. And because D0 is the divisor that we're working with, D0 must be less than or equal to D. And remember, we can now go back to what we defined D0 and D as, which is the greatest common divisor of B and R and the greatest common divisor of A and B respectively. So now we can conclude that the greatest common divisor of B and R and the greatest common divisor of A and B is, the GCD of B and R is less than or equal to the GCD of A and B. So cool, that's our proof. But as an extension, or also make sure that you conclude your proofs with either QED or white box or black box, just to indicate your proof has been done. As an extension, you can also prove that the GCD of A and B is less than or equal to the GCD of B and R. And once we prove that, we can show that the GCD of B and R is the same as the GCD of A and B, right? Because of this inequality signs that works both ways. And once we prove that the GCDs are equal, we can use that in our Euclidean algorithm. Okay, so now we're going to work with these, I guess, a bit easier questions. We're just solving the congruences of these equations. So to figure out if they have a solution, first we need to cite Bezout's theorem, which is that if we have this equation, x plus by equals c, if c is if c is a multiple of the greatest common divisor of a and b, then the equation will have an integer solution. But otherwise, if c is not a multiple of the greatest common divisor of a and b, then there's not going to be an integer solution to x plus by equals c. So if we use that over here, we can see that the greatest common divisor of 14 and 21 is quite clearly 7, right? And because 7 is a multiple of 7, then there is a solution to the first question. But with question B, we can see that 5 is not a multiple of 7. And because of that, this congruence has no solution. And just like A, question C also has a solution because 0 is in fact a multiple of 7. Now I just said that the GCD of 1721 is 7, but we can actually go further and sort of work with Bezout's theorem a bit more closely. So for each of these, we're proving that 14x is equivalent to n has a solution. And by the definition of modular arithmetic, we can rewrite this as 14x equals to 21k plus n for some integers n and k. And so if we do a bit of rearranging, we can put it in this form: 14 times 1 plus 20 times by minus k equals to n. So if we sort of like see that it's in the form of x plus by equals c, where a is 14 and b is 21, this is exactly like Bezout's theorem. So we can use Bezout's theorem and say that because, I guess for part A, because 7 is a multiple of 7, which is GCD of 14 and 21, there is a solution. So now let's go on to actually solving these congruences. we can start just by dividing everything by 7, because that's something that comes out of modular arithmetic. If we have, I guess, 14x is equivalent to 7 in modulo 21, if all those numbers are divisible by a common divisor, then we can divide through, an integer divisor, obviously. And we can divide all the numbers through by that same number. So in this case, we're doing 7, and we get 2x is equivalent to 1 in modulo 3. Now, there are a couple of ways we can solve this. Does anyone have a particular way to this question, congruence? No? Okay. So, a possible way that you can solve this is by doing the extended Euclidean algorithm, right? So you rewrite it as 2x plus 3y is equivalent to 1 or something like that, and just solve it by the extended Euclidean algorithm, which I'll show you later. But we're not going to do that here because if you haven't noticed, these numbers are quite small. So basically, we just test numbers. Does anyone have a number which they want to test here? Yeah. 2. Okay. Let's see if that's right. I know it's right because the next working out is this. Right, guessing x equals to 2 works, right? So we know that 2 times 2 is 4, and that's equivalent to 1 in modulo 3. So also we found a solution. So our solution would be x equals to 2 in modulo 3. It's important to write modulo 3 and not 21 because if we wanted to expand our solution set, if we wanted to do it in modulo 21, we'd have to expand our solution set, which I'll show you guys how to do that later. Now let's do this question. Yep, we can't do it, so we just write no solution. And let's do this one now. This one's, I'm not going to take too much time going through this one because it's quite similar to part A. Instead, we're actually working with even easier numbers. So as we did in part A, we just divide everything through by 7, and we get 2x is equivalent to 0 in mod 3. And I guess it's even easier to guess numbers now because 0 times any number is just 0, so we can guess x equals 0, and that works. So pretty cool. Yeah, so we can also extend the solution set, which I'll teach you guys in a bit harder example, which is this one. Okay, no worries. All right. So now we're going to solve this congruence 39x is equivalent to 15 modulo 57, where they want us to give our answer in 2 possible ways. So the first one is a congruence to the smallest possible modulus, and one where we don't change the modulus at all, which is just 87. Okay, so how are we going to do this? Okay, so as we did before, like in the previous question, we found that there is a common divisor between all these numbers, which is 3. So if we divide every number by 3, as you can see here, we get that 13x is equivalent to 5 in modulo 29. And now we want to find the greatest common divisor of 13 and 29, which, can anyone tell me the answer? Yeah? Oh yeah, cool. Just 1, right? But we want to actually still find it manually because that way we can apply the Euclidean algorithm. So as you can see here, now we're using our division algorithm, which we had a look at before. So A equals to B Q plus R. And that means we could write 29 is equal to 2 times 13 plus 3, right? And because of what I was sort of showing before, if you have A equals to B Q plus R and everything is an integer, we can write that the GCD of A and B is the GCD of B and R. So in this case, A and B are 29 and 13, and B and R are 13 and 3. So now we can just move on. So we can just keep going. So 13 is equal to 4 times 3 plus 1. So now our A and B have transferred to the B and R, which is 13 and 3. And our new B and R is 3 and 1. And the GCD of 3 and 1 is just 1. Yeah. Okay. So there is that's the greatest common divisor of 29 and 13 is 1. And there is a solution to the congruence as 1 divides 7. That's okay. Wait, sorry, is this an old version? Because I edited it. Yeah, I edited it today. That's why it's not. Can I jump on that? Because it's much nicer. Sorry, there's technical difficulties right now. Okay, yep, so we're just using a new, more published version of this PDF here. Okay, yep. So as we saw before, we could write, now we want, the idea behind the extended Euclidean algorithm is that we go back on what we did in the actual Euclidean algorithm. So that we can find numbers such that we get this form ax plus by equals c, where y is usually the modulus, so that when we take the modulus of everything, we just get ax is equivalent to c in the modulus that we want, because by would just be cancelled out by the modulus. Okay, so if we go back to here, we can see that 1 is equal to 13 minus 4 times 3. So let's write that. And the idea behind this is we want a and b to stay the same. So a and b would be 13 and 29. And we could rewrite 3 as, I guess, a combination of 13 and 29. So as we saw here, 29 equals 2 times 13 plus 3. So if we sub in 3 equals to 29 minus 2 times 13, we can get that 1 is equal to 13 minus 4 and that stuff, right? Which is just 3. And just doing a bit of rearranging, we can get that 9 times 13 minus 4 times 29 is equal to 1. And this is basically in this form x plus by, where a is 13 and b is 29. And so if we take the modulus of this whole equation here, we can get that 9 times 13 is equivalent to 1. But is 9 our answer? Someone please answer. No, right? Because when we go back here, we want to find the solution to 13x is equivalent to 5, right? And so what we can do here is we can just times 5 by everything. So we get 45 times by 13 is equivalent to 5 in modulo 29. And just by simplifying our answers, we know that 45 is equivalent to 16 in modulo 25. Just by minusing 29, yeah.
So is x plus by equal 1?
X plus by. Sorry, ax plus by is equal to 1, yep.
Is that equal to 1?
Are you asking if c is equal to 1?
Oh no, so is c not equal to 1?
Yeah, so c can be any multiple of the greatest common divisor of a and b. So in this case, it can be basically any integer, right? Because 1 is the GCD and every integer is multiple of that. Yeah?
So when you x plus by equals c,
yeah.
Right? So x plus by doesn't equal 1.
In this case, we can let it be 1, just so we can find out our integers. And once we have an x and y that satisfy it in order for c to be 1, we can just times everything by 5, so we can get 5, right? So our x would be reality 5x, and y would become 5y. Yeah? Okay, cool. Yeah, so our solution would be 16 because 16 times 13 is equivalent to 5 in modulo 29. And remember that this question was asking for the smallest modulus, right? Which is 29. Now the second question is asking us to put our answer in modulo 87. So how do we do this? We know that in modulo 29, x equals 16 is a solution. And we can expect that in modulo 87, there's going to be 2 more solutions because at the start of this question, we divided everything through by 3. So we can see that in modulo 29, x equals to 16 is equivalent to 45, which is equivalent to 74. But this is all in modulo 29. So as long as x, in this case 16, 45, and 74, satisfies the congruence 13x is equivalent to 15 in modulo 87, which we basically solved in the previous question. Because it satisfies this, then it will also satisfy the answer in modulo 87. So we can see that our set of solutions that we have in modulo 87 are going to be 16, 45, and 74. Is there any questions on that? No? Okay.
Is that meant to say modulo 83 or 87?
That's a good question because that's supposed to be 87, sorry. Yeah. Okay, so now let's do another question which is from a different part of chapter 2, which is let tilde be the relation on a set of integers z defined by a is related to b if and only if a squared is equivalent to b squared in modulo 4. So first we need to prove that tilde is a equivalence relation, and then we need to find the equivalence classes of tilde. Okay, so can someone tell me what things we need to prove in order to prove that this relation is an equivalence relation? 3 things? No? Okay.
Reflexivity.
Yeah, reflexivity. Transitivity, yeah. And
Symmetry.
yeah, symmetry. Awesome. So as long as we prove those 3 things, we can prove that it's an equivalence relation. Okay, so the idea behind reflexivity is that we just want to show that if we have an a, which is in this set of integers, that if it satisfies this relation, then a is related to a. Basically, that's reflexivity, right? So in this case, we just want to show that a squared is equivalent to a squared modulo 4, right? And I guess if you just look at it, it's pretty easy. I guess in an exam, I'd probably start off by, I guess what I like to do is I like to start off with a universal truth. So in this case, I'd start off with a is equivalent to a in modulo 4, right? That's pretty universal, right? And we use a property of modular arithmetic, which is saying that we can take the power of both sides and it remains the same. So in this case, we wanted to take the power of the second power. So we say that a squared is equivalent to a squared in modulo 4. And so this is just a nice proof to show that this relation is in fact reflexive, right? And we prove that, and now we're moving on to symmetry. Okay, and the idea behind symmetry is that if A is related to B, then B is also related to A. So it works both ways, okay? And how are we going to do this? So we start by, question? Yeah. Did you have a question? No, you did not. That's okay. Okay, cool. Let's move on. Yeah, no worries. So with symmetry, antisymmetry, and transitivity, it starts off with you having to assume something. So in symmetry, we have to assume that A is related to B, right? And so that now we're trying to prove that B is related to A. So if we assume that A is related to B, by the definition of our relation, then A squared is equivalent to B squared in mod 4. And again, right, we can kind of sort of just already see that B squared is equivalent to A squared in modulo 4. But let's go back to the definition of modular arithmetic to help us do a more thorough proof. So we know that now A squared is equal to 4k plus B squared for some integer k because of the definition of modular arithmetic. And if we rearrange terms to get B squared as subject, right, because that's what we want, we just wanted to move that in this one equation, a squared equals to b squared mod 4, we wanted to move this b squared to the other side. So from this equation, we rearrange it so that we get b squared equals to a squared minus 4k. And again, we take the modulus of everything. And now we can just get that b squared is equivalent to a squared mod 4. So basically the idea behind this argument is that we prove that if a is related to b, then b is related to a, which you do by assuming that a is related to b, and then from that you prove that b is related to a. So symmetric. Now let's move on to the final part of our proof, the transitivity. And like I said with symmetry, you got to assume some stuff in order to prove some other stuff, right? So in this case, we assume that if a is related to b and b is related to c, then a is related to c. Yeah. So an example of a transitive relation is, I guess, any inequality operator, right? So if a is less than c and if a is less than b and b is less than c, then a is going to be less than c. Yeah. Okay. So let's assume a is related to b and b is related to c. And so by our definition of the relation, we get that a squared is equivalent to b squared in mod 4, and b squared is equivalent to c squared in mod 4 as well. Okay? And like we did with symmetry, let's go back to our definition to make a more thorough proof. So we're, I guess, letting a squared equals to 4k1 plus b squared and b squared equals to 4k2 plus c squared. Okay, so now we want to prove that a is related to c. So we want to write it such that a squared is equal to 4 times some random integer k plus c squared. Does anyone have any ideas of what we should do next to get that?
Substitute b squared.
Yeah, right? So, like, b squared is even the subject in the second equation here. So it's really nice if we just substitute it. So if we substitute the second equation to the first equation using b squared, we get that a squared equals to 4k1 plus 4k2 plus c squared. Okay? And as you can see here, we can just factorize a 4 out. And now we can just basically say a squared is equal to 4 times some random integer plus c squared, which is what we wanted, right? Because if we take the modulus of 4 on both sides, we get that a squared is equivalent to c squared in mod 4, not equal to. Yeah. Okay? And so we've proved that if a is related to b and b is related to c, then a is related to c. And so it's transitive. And now that we've collected these three parts, transitivity, reflexivity, and symmetry, we can conclude that our relation is in fact an equivalence relation. Okay? Now let's find the equivalence classes of tilde. Does anyone remember what equivalence class is? No? Okay, that's okay. So the idea behind an equivalence class is if we have some, I guess, element of the relation, we want to find every other element that is related to this one element, as you can see in this more formal definition here. So if we go to finding the equivalence classes of our relation, we have to first, I guess, look at what we're dealing with here. We're dealing with the set of integers z, and that's an infinite number of numbers, right? But let's not be afraid and see that we're actually dealing with every integer in modulo 4. So we know that all integers can be reduced down to a value within modulo 4, so 0, 1, or 2, or 3, right? And so now let's test numbers. When a equals to 0, a squared is also equivalent to 0 in mod 4. So we know that every integer that is a multiple of 4 is going to satisfy this, because every integer that's a multiple of 4 is 0 in modulus 4. Okay? So we can see that all these multiples of 4, 8, 0, minus 8, 0, 4, 8, 16, are all part of this equivalence class of 0. And so we formed one equivalence class. Let's move on to when a equals to 1. Just a reminder that we only need to test 4 values, 0, 1, 2, and 3, because remember that all integers can be reduced down to these numbers. Okay, so when we use a equals to 1, we get a squared is equivalent to 1 in modulo 4. And so if we get any number that is, I guess, 4 times an integer plus 1, so we're just saying that if this integer is equivalent to 1 in modulo 4, then it's going to be in this equivalence class. So that would be minus 3, all these numbers here, minus 3, 1, 5, 9 is not 7. Okay? And so now let's move on to the third value that we're testing, a equals to 2. And we see that a squared equals to 4, which is quite nice because it's actually equivalent to 0, right? And can someone tell me why it's nice that a squared is equivalent to 0 in this case?
You found a repeat?
Yeah, awesome. So now we know that every element that's related to when a equals to 2 is also going to be part of one of the classes that we had earlier. So now we're just dealing with all these integers which are equivalent to 2 in modulo 4. Okay? Yep. So that this 0 should be a 2. Sorry for the typo. Okay. And that means similarly when a equals to 3, a squared equals to 9, which is equivalent to 1 in modulo 4. So every integer is equivalent to 3 in modulo 4. And again, we found a repeat, right? Because when a equals to 1, the a squared is also equivalent to 1. So we can see that here, where now the equivalence class of 0 will contain when every integer that's equivalent to I guess 2 or 0 in modulo 4. So that's basically all the even numbers, as you can see here. And similarly, 1 will contain all these numbers that we got from when a equals to 1 and a equals to 3, i.e. all the odd integers. Okay, so now we found our equivalence classes. Yeah. Now let's move on to this, I guess, much more complex question, right? It's got a lot of text and a lot of numbers. And so basically, first we define a set. And the set is a set of tuples. So I guess 3-elemented tuples. Every element of the set will have 3 elements within itself. And these elements will be numbers. And it's defined by every set of 3 elements. So each 3-elemented tuple is defined by this equation here, where x1 plus 2x2 plus 3x3 is equal to n. Okay? So I guess that's a bit much to work with right now, but we'll see a better picture of that later. And also define this relation on the set by if you have a tuple if a tuple is related to another tuple, then that x2 value must be less than or equal to that y2 value, and that x3 value must be less than or equal to that y3 value. Okay? So our first question is asking us to draw a Hasse diagram for the relation when n equals to 5. So it might be a bit complex at first, but let's just first try to find the set S5. Okay? So as you can see, we just have this equation here. And we want to find x1s, x2s, and x3s that satisfy when n equals to 5. So I'll give you the first example because then you can sort of see what this question is all about. If we have the integers 0, 1, and 1, they satisfy this equation here because 0, when x1 equals 0, and x2 is equal to 1, and x3 equals to 1, we have that 0 plus 2 times 1 plus 3 times 1 is equal to 5. So that satisfies our definition of the elements within the set. Okay? Does anyone have any questions about that? No? Okay. So because we need to find the elements of the set manually, let's do it in such a way that is systematic, right? We can start by just looking at this x1 and starting off with 0 and moving our way up to, I guess, the maximum possible number, which is going to be 5. Because once we have x1 equals to 6, we're going to exceed n, which is 5 right now. So we let x1 equals 0, and then we moved our x2 up by 1, so it becomes 1, and x3 is also moved up by 1, which it becomes 1. And we found our first set, which is 0, 1, and 1. Now, if we move x2 from 1 to 2, we get 2 times 2, which is 4. And there's no way we can get another 1 from 3 times x3. Okay? So that means we have to move on to when x1 equals to 1. Over here, there's also only one solution. So when x2 equals to 2 and x3 equals to 0. So let's pretend like there are solutions, okay? So if x2 is also 0, but x1 is 1, then we'd have 1 plus 0 plus, we need 4, right, to complete the 5. And we can't get a 4 from 3 times a number. So all we're dealing with here is we're looking at if we can get multiples of different numbers to add to each other to get 5. And so if we find the remaining sets, so 2, 0, and 1, and also 3, 1, and 0, okay, we can conclude that our set is actually this. So 0, 1, 1, 1, 2, 0, 2, 2, 0, 1, 3, 1, 0, and 5, 0, 0. Okay? And does anyone have any questions on how I found that set? No? Okay. Yeah, all good. So now we want to draw a hash diagram, right? Which is basically several nodes that are going to be connected together based on whether they're related to each other or not. So we want to find which tuples are related to each other. And remember that two tuples are related to each other if the x2 value is less than or equal to the y2 value and the x3 value is less than or equal to y3 value. So it's nice, it'd be good to, I guess, list out, make this table of x2s and x3s just so that we can compare the nodes. From this diagram here, can you guys see any two nodes that are going to be related to each other? No? Okay. Well, if you have a closer look at E, E has the values of 0 and 0 in its x2 and x3, which means because 0 is going to be less than or equal to any other value of x2, and x3 is also going to be less than or equal to any other value of x3, we can conclude that E is actually going to be related to all these other nodes, okay? And we just need to keep going, so we move up by having a look at all the other nodes. If you look at D, the x2 value is 1 and the x3 value is 0. Now, D cannot be related to C. Can someone tell me why? It's because 1 is not less than or equal to 0, as you can see here. But the x3 condition is satisfied. But we need both of these conditions to satisfy for the two tuples to be related. Can someone tell me if D is related to B? Yeah, right? Because 1 is less than or equal to 2 and 0 is also less than or equal to 0, right? And we can keep going. So B is not going to be related to anything because 2 is actually the highest value of x2 in this set of numbers, okay? And we can also see that C is going to be related to A because 0 is less than or equal to 1 and 1 is less than or equal to 1. So now we've found, I guess, all the relations, the relationships within this relation, right? Where E is related to A, B, C, or D, and D is related to A and B, and C is related to A. So how do we put this in a hash diagram? Okay, so we can do this, this is just a solution, but we start off by having, finding the greatest node of this set. So in this case, the greatest node is defined by where no other where this node is not related to any other nodes. So in this case, it would be A and B, right? So if this was an exam, you'd be drawing the hash diagrams. You start off by drawing A and B at the top here. And then you'd go and draw, the next greatest, right? Which would be D. And because of how hash diagrams work, you'd connect D to A and B. as you can see here. And then you just keep going down this ladder, and you see that C is also sort of the greatest, the next greatest, right? Because C is related to A. So you draw like this line here. So right now, you'd have this line connecting AC, this line connecting A and D, and you have this line connecting B and D, right? And we know that E is related to everything. So let's draw this E down here and connect it to, well, you can start by connecting it to everything, right? A, B, C, and D. But the idea behind Hasse diagrams is that we're simplifying this relation. And because we know that, I guess later we prove that it's a partial order, right? We can show that the idea behind Hasse diagrams is that we remove the lines that indicate transitivity, right? Well, these lines, just this connectedness also already indicates transitivity. So we know that, I guess later, right? E is related to C and C is related to A. That means E must be related to A just by transitivity. And so we don't need to draw this line between A and E, nor do we need to draw this line between E and B. But we need to draw the line connecting E and C just so that we have that relationship there. And also we need to connect E and D. Okay? So now let's get on to proving that this is a partial order. Okay, can you guys tell me what I need to prove in order to prove that this is a partial order?
Beta symmetry, transitivity, and
Yeah.
reflexivity.
Yeah, so it's basically the same thing as, not basically, but like almost the same thing as proving an equivalence relation. So first we need to prove reflexivity, and we need to prove reflexivity and transitivity. But the difference between equivalence relations and this partial order is the second one, which is proving that it's asymmetric rather than symmetric, which is what is needed in equivalence relationship. So let's start by proving reflexivity, right? We suppose that we have a tuple in the set, right? Such that x1 plus x2, x2 plus 3x3 is equal to n, right? For some integers x1, x2, x3 larger than or equal to 0. That's another typo. Apologies. Okay? And so by our definition, right? Well, actually, we just know that x2 is less than or equal to x2 and x3 is also less than or equal to x2, right? And we're trying to prove that the tuple x1, x2, and x3 is related to the same tuple x1, x2, and x3, okay? And because we know that this is in fact an element of the set, we know that these two tuples are actually related to each other because they satisfy this one condition, that x2 is less than or equal to x2 and x3 is less than or equal to x3, okay? So that's a pretty simple proof. Now let's move on to asymmetry. Does anyone remember how to prove asymmetry? That's okay, because I remember. Okay, so in order to prove asymmetry, you're trying to prove that if A is related to B and B is related to A, then A must equal to B, right? If you guys remember those diagrams dealing with relations, it's the one where there's no double loops, lines between two nodes, okay? So we start off by assuming that A is related to B and B is related to A. So in this case, it's not A and B, it's the tuples x1, x2, and x3, and the other tuple would be y1, y2, and y3, right? And it's for the integers that are larger than or equal to 0, not less than or equal to, okay? And so by our definition of having these related, we know that x2 is less than or equal to y2, and x3 is less than or equal to y3. This is by our first assumption at the top here, okay? And by our second assumption, we know that y2 is less than or equal to x2 and y3 is less than or equal to x3. By these two, I guess, ideas, right? These two, the blue colored and the red colored. Can someone tell me what we can conclude from these two ideas?
X2 and Y2 are equal and X2 and Y3 are equal.
Yeah, right? So x2 must be equal to y2 and x3 must be equal to y3, right? So we've already, started proving that these tuples are in fact the same by proving that x2 and x3, x2 is equal to x3, y2, and x3 is equal to y3. So that's pretty cool. But what else do we need to prove? We need to prove that x1 is equal to y1. So to do that, there's one thing that we haven't really used yet in this one proof. We haven't used our definition of the tuples in the set, which come down to this line here, where x1 plus 2x2 plus 3x3 is equal to n. And because this tuple of y1, y2, y3 is also in the set, it satisfies this equation too, that y1 plus 2y2 plus 3y3 equals to n. Okay? And so let's equate these, right? As you can see in this line here. And what can we do? Why can we do this, right? Why can we get from this line to this line? Can someone tell me? Yeah. So we already know that x2 equals to y2 and x3 equals to y3. So if we just minus it off from, this equation, we can get that x1 equals to y1. And so we've proved that these tuples are the same and the relationship has to be asymmetric. Okay? And so now we need to do our final part, which is transitivity. Now we're just trying to show that if this tuple here, x1, x2, and x3 is related to y1, y2, y3, and y1, y2, y3 is related to z1, z2, z3, then x1, x2, x3 must be related to z1, z2, z3. Okay? That's a lot. But it's pretty simple because from our assumption, we can see that x2 is less than or equal to y2, and x3 is less than or equal to y3. But we also know that y2 is less than or equal to z2, and y3 is less than y3 is less than or equal to z3. And can someone tell me why we can conclude that x2 is less than or equal to z2? Yeah. No. Well, this is actually quite interesting because now we're just using the transitivity of this operator less than or equal to, right? Because it's just given that this operator is transitive. That means we can conclude that x2 is less than or equal to z2 and x3 is less than or equal to z3. And so if we go back to our definition of, relations, the relationship between two tuples, we can conclude that x1, x2, and x3 is related to z1, z2, and z3. And so now that we've proved that it's reflexive, asymmetric, and transitive, the relation is in fact a partial order. Okay, so this question is not necessarily modular arithmetic or relations. It's more to do with the first part of this chapter, which is to do with integers, right? So let m be the product of all primes between 10 and 20. Let n be the product of all the numbers between 20 and 30 inclusive. What is the greatest common divisor of m and n? And also we need to find the highest power of 10 that divides n. Okay? So in order to find the GCD of two numbers, we look at the primes, right? We need to identify the primes of this number and see how many primes does m and n have in common? Because then that would give us our greatest common divisor, right? And so it seems sort of useless if we were to look at n, right? Because n has heaps of primes. We have 20, which by itself has 5, 2, and 2. 21, which has 3 and 7. And just all these numbers, the prime factorization of n is very large. But we're just looking for the primes that are in common, right? And because we know that m is defined by the product of a few primes, which in this case we found to be 11, 13, 17, and 19, we just need to look at the primes of m and see, are these primes of m in n as well? And in fact, not all of them are, but some of them are. So let's first look at 11. Is 11 going to be in n? Can someone tell me? Yeah, because of this one number 22, right? 22 is factorize into the primes of 2 and 11. So 11 does divide n. And similarly with 13, we can see that 13 divides 26, which is also a factor of n. But unfortunately, no multiple of 17. So 0, 17, 34, and so on. None of these numbers are included in n. So 17 does not divide n, and neither does 19 by that same reason. And so now our GCD would just be the product of the primes that we can find in both m and n. So in this case, it was just 11, 13, which is 134, 143. Okay. Now let's find the highest power of 10 that divides n, okay? To find the highest power of 10 that divides n, we want to find, if we were to factorize n into its prime factorization, how many times would we find 10? And we wouldn't actually be able to find 10 at all, right? Because 10 is not a prime number. So to do this, we need to break down 10 into its primes, which are 2 and 5, right? So let's look at n. So for every 2 and 5 that we have within n, we can get a 10 from that. So it's like collecting, right? We can look for both 2 and 5, but it's more reasonable to just look for 5, because within our prime factorization of n, we're going to have heaps of 2's and not a lot of 5's. And we need these 5's in order to make a 10. If we don't have a 5, we cannot make a 10. Okay? So if we look at the product, right, that we had before that was defining n, we can see that there are in fact 3 numbers that 5 divides into. And these are 20, 25, and 30, okay? And from this, we can extract primes of 5 from this. And when we extract it, we can get this 5 here, these 2 5's, and this 5 here. Just by, factorizing the 5's out of these blue numbers. And if we extract all these 5's to the side, we get 5 to the power of 4. So that means we need a 2 to the power of 4 to match that 5 to the power of 4 to get, 10 to the power of 4, or just 10's in general, right? And 2's aren't, as I said before, they're not really hard to find in the sequence, right? Because 4 will give us 2 2's, 22 will also give us a 2, 24 will give us lots of 2's as well, and the number of 2's will definitely be larger than 4, okay? Just because we also have lots of even numbers here, okay? And if we extract the 2's out, let's extract these 4 2's out, these particular ones. We get that 5 to the 4 times 2 to the 4 times some number is equal to n. And note that these numbers on this product on the right, not including the 2 to the 4 and 5 to the 4, no 5 would divide into this number because we've extracted all the 5's out of this number. Okay? Does anyone have any questions so far? No? Okay. So now that we have all these 5's and we have these 2's, we can just combine them and we get 10 to the 4. And just a reminder again, because we have no 5's within this product here, we can't collect any more 10's. And so the highest power of 10 that we're gonna find in this number is in fact 4. Okay? Yeah. And just note that again, this integer n, this product here, does not have 10 as a factor because it doesn't have 5, which is necessary to make that factor of 10. Okay? And this concludes our awesome lecture. Yeah, good luck for your exams and hope to see you next time. All my relationships are asymmetric.